You have a set of keys, and they are not sorted, but I can still define for every key the rank of this key. That is how many elements are smaller than it. And I want to find, let's pick delta to be n half. I can do it because I can pick delta to be n half, and remember n in this question was power of 2, and delta was power of 2, so they nicely divide in each other. And I'm asking you, can you find the element which is, for I equal 0, it would be the first element. For I equal 2, it would be the last element. And for I equal 1, it would just be the half element with rank of n half, making it a median. And the time to do it is order of n, expected time, or n log of, what is this? Log of n minus n, yeah, it's, minus of the logs is like dividing the arguments, log of n divided by n divided by n half. That should be the running time, which makes it order n. And I'm asking, can you find the median in this time? Expected this time. And the answer is yes. You had an algorithm just after we covered quicksort. We said we can use the same idea of the quicksort just to find the median by picking the pivot and then either branching on the left side of the array or the right side of the array, but not both of them. And that's how we can find the median in expected linear time. And if I can find the median in expected linear time, then I can now make another iteration and find 2 more guys, actually 5 guys, over here, nicely split by delta. And if I'm still, right, because now it would be just the time on the left side after I found the first median, it would be the time on the left side, the real median, and the time of the right side. And then I'll find the median of each one of them, and so on. And you'll make the math, and that's exactly the logs that you are looking for. So that was the answer to this question in the midterm that use the median algorithm. That's, I think, that people with a sorted array people did very well. The skip list question that people are still confusing about this question with the skip list. What is a search time, which is the only interesting question here. The other question just kind of built up into it. The only interesting question is what is a search time in a k-perfect skip list. That is, if I'll do it, if I'll jump 1,000 elements and promote one, make 1,000 elements stays in level 1 and then promote one of the last one. Jump 1,000 and promote. Will the running time be smaller or larger than the time in a normal skip list? And the answer is, see, let me rearrange the camera, please. And I have this part covered, and I have this part covered as well. And it's true that in a k-perfect skip list, number of levels is order of log to the base k of n, which creates the illusion that if the larger k is, I'll have fewer levels, so the search time will be smaller. But it's not really true, not in the worst case at least, because in each level, I might spend k time, so that's the number of levels, but search time will go up to order k times log k of n. But in every level, I might spend k time, making it less efficient. So 1,000 skip list in general will take more time. 1,000 perfect skip list will take in general more time than 2 perfect skip lists. Okay, that was about the questions from here. Homework 4 was overlapped with these questions a bit, and I asked in homework 4 also to find the longest string or approximating the longest string that match into 2 sequences. Everybody submitted so far. I understand that I screwed up with the setting of a grade scope, but hope by now everybody is good about submitting. Great. And yeah, I think that by now the reaction I heard suggested that people did figure out that if I have 2 strings, I don't have much luck with markers. So inside T1, I have a substring started at index I. That is, this window starts at index I. And for the moment, let's assume that M, the length of this substring, is known to us. It was a hint that I added for this question. And in T2, at index J, I have the very same window. Just start at a different place. The very same window, also with length M, exactly the same M. I just don't know what is I and J. So people try to use suffix tree, which is a very cool data structure. You can build it in n square time. You can build it in linear time with a bit more tricks. It's basically a suffix, somehow compressed version of twice. And they try to use it, and it's not a bad idea. If M is very short, then what you can do is build the suffix tree once. If M is very short, build the suffix tree once. Suffix tree is a data structure, maybe we'll talk about it, that takes the whole text, and now you are taking a substring and ask where is the substring appears in the whole text. And that's a deterministic data structure. It never makes any errors. So the attempt was build the suffix tree for T and then check all the windows of all the starting position of J inside T prime. It's OK if M is very short, and it will run in linear time in this case. Problem starts when we take M to be a bit longer than log M, for example. Because every time that I put the window here and I put the window here, I need to scan all the characters inside the text. Yeah?
I don't know about suffix tree, but when I read about it in Wikipedia, what they did is that they add a special character, for example, 1 or 2 at the end of each string, and then they make one suffix tree for both of the string, and then find the deepest node that the subnode contains both 1 and 2.
Oh, OK. And it's all in linear time?
Yeah.
I'll take a look. If you find a solution that covers it completely and you explained it, you are good. I'm not. It's not what I had in mind, but if it works, it works in linear time for every M. No, again, where my thought about this problem was, of course, recycle Rabin work, which means I will look at all the shifting of the window, all the possible eyes. Each one suggests a value, which is very long when I think about it as a number, but I can hash it. How? In the same way that Rabin hashed it, do modulo Q. And once you're doing it modulo Q, then every shift of the window from putting the window at I to put the window at with the same length starting at I plus 1, shifting the window takes a constant time, according to Rabin, because you're doing modulo Q, so all the operations are done all in modulo Q, and you're working on a much smaller number. Numbers that you can have only log n many bits. So your computer is able to do it in constant time. So you're producing the hash value for every I, that is age of the window starting at 1, age of the window starting at 2, all the way up to age of the window started, what would it be, n minus m. I'm not writing exactly what is age, but you understand it's Rabin when this is the window that I'm looking at, the length of the string that I'm looking at. And from now on, it continues like the question about the files. I look at all these hash values, and I stack them in a hash table. So here is age of 3 and age of 22. Okay, and now I'm doing the same trick on T2, except that I'm not inserting into the hash table. I'm checking if this value appears anywhere in the hash table. And it also takes linear time. Now, that's randomized solution. If you want to be serious in your answer, to be perfect in your answer, you also ask what's the probability of a false positive. And Rabin makes the analysis about if I just have n strings that I match. Here I have n square strings that I match. So you want to ask, out of these n square strings, how can I bring the false positive probability to something that I'm willing to accept? And you look at a set of primes. You're saying, out of all these primes, how many of them participates in all the n square many values that you are producing, n square many values, and follow Rabin word by word. You're asking about the probability. And now if I pick a random at random, can I bring the false positive case to less than 1 over n, or 1 over nn? Which will mean that even if you are using, say, the tries or just checking for false positive, false match, character by character, if they fit, you'll do it no more than a constant number of times for the whole string, so it doesn't cost you too much. No. Okay, but I'll accept it if you just say something about the hashing plus plus member something about why do you think that the probability of false positive is low. Essentially, did you understand Rabin including the proof or not? That's where this question was trying to lead. Now, other trick to take from this question is that now you don't know m exactly, but I didn't ask you for the running time exactly either. I asked for try to be as efficient as possible. So here my attempt would be try, if you think that m is relatively small, try a string of length 1 over 0.9, which is roughly n plus 1 plus 1. Let's call it 2. And then I'll try 1 plus 1 square and 1 plus 1 cube, dot, 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 1 plus 1 to the power of log to the base 1 plus 1 n. That is, you're just looking for lengths of log n many possible lengths of m. Looks very strange. It will be more digestible if I'll replace the 1 plus 1 by 2, so I'll try strings of where m equals 2, then 4, then 8, then 16, 32, and so on. We'll see in a moment why this list is maybe better. Now, what are we saying about the hashing? If I am wrong about m, and I take m to be slightly too large, I lost everything. I take m to be large, then maybe there is a matching of 100 characters from here and 100 characters from here that match exactly. But if I'm trying to hash anything that is just above 100, 101, this extra character here, which would be A, and the one extra character B over here, that would be B, once I'll take the length as 101, the hash value are completely different. I have no control about it. That's exactly what hash functions do for us. So if I'm overshooting to be too long, I get no meaningful information. But if I undershoot and take m to be a bit too short, so it's not 100 character, it's 99 character, then the hash values will still match. So I didn't find the longest string. If that's the only length that I check, then I'll find a string who is half the length of the optimum. Agree? We'll find a substring that is at least half the length of the optimum. Because the match that I will find will only use 50 characters, and you know that there are 100. 50 is not good, 51 characters, but you know that I can find 100. Okay? Now, why do I prefer this sequence instead of this sequence? Is because this is still tells you just have to check at most log m many values. You stop once you find, once you take a length of m which is too long, you stop. But you're trying longer and longer, but they grow exponentially. Each time I multiply by 1 over 90%. So the strings that I do find is at least 90% of the opt. And of course, you can trade off anywhere between the 100% and 99. You have more tries, but it's only logarithmically here in the constant. OK, so that's about the two strings questions, which, once again, I'll accept, of course, other solutions. My intention when I gave this question was just, are you mixing the solutions to rubbing that you need to understand for doing it, together with a solution of essentially the identical files. OK, I think that as far as talking about the skip list and the homework and homework 4, there was something else in homework 4. Yeah, this question that some people had problems with, which of course you cannot see, but before I go through it, this question is actually coming, how many levels in a 2-level skip list, is actually coming up from an interesting puzzle, cute puzzle that I'll tell you the old version and no, I'll tell you just a new version. You have a building. This building has n many floors, and you have 2 cups. And for each cup, the same height for each cup, there is some floor k that if you drop this cup down to the floor from height k, it will stay safe. If you drop it from height from story k plus 1, it will break. Again, there is a maximum height at which each one of the cups will stay safe. go anywhere above this height, and it will 100% break. How, with only 2 cups, can you find this value k? That's a puzzle that it's coming from. Okay, like one solution would be go to the floor one after the other, one by one, and then your problem is just that you should have said it, that you want to minimize how many times you need to go up and down the building. You want to find what is this value k, this optimum k, as fast as possible with fewest number of bring the cup up and down. So we all know about binary search. Binary search will mean that you just have to go log n time, which is kind of the optimum, but that implies that if I overshoot in my height, if k is less than the optimum, then I got rid of one of this cup. And my next error of overshooting will get rid of the other cups, and I don't have any more supply of cups. If I'm just going through the floor one after the other, I'll get to the optimum k eventually with only one cup. That's the other extreme. But that implies that for every floor, I need to go up and down. The optimum solution is up to constant, jump by square root n. Jump by square root n until you find the correct height with square root n. Maybe you sacrificed one cup. And then when you identify that the solution is somewhere between this flow and this flow, which has only square root n many stores is between it, between this one and this one, how do I know that that's a maximum? Because I wasted one cup, but I still have one cup to play with, and then I need to go up and down only square root n many levels until I can use the other one. Okay, so that's a solution that has square root n solution, and that's exactly like skip list with 2 levels. And when you are preparing for your next interview, you can ask yourself, what happens if you have 3 cups? It's very natural here. What would be my best strategy if I have 3 attempts? Or a skip list with 3 levels? When will your search time be the maximum? Right, and the same goes here when I'm asking of I didn't ask it specifically, but if I'll tell you that you just have 2 levels, and you design any skip list, you decide it anywhere you want, but you only have 2 levels. The lowest one is sequential. Everybody is in it. So you essentially have just to pick where are the elements of the second level so that the query time will be as small as possible. And check for yourself, it's a good exercise, that if I'm trying to minimize the search time using 2 levels, my best strategy is to space the second level in jumps of square root n. Okay, so here essentially I gave you the solution to the problem, but the question that this answers to is how would you generate a 2-level skip list that has a minimum worst case query time? Again, how would you minimize, if you have only 2 levels to play with, design a skip list that has a minimum worst case query time. You can show that if you're doing anything but spacing them as square root n away from each other, then me as a vicious adversary will, say, here is my lowest level of the skip list, level 1. And here are the elements at level 2. And you are leaving a gap here which is larger than square root n many elements. What will I do as a vicious adversary? Prefers a query of this guy over here, which will mean that you have to go all the way from here, go down, and then scan all the elements on this level. And what will I do as a vicious adversary if you are using more than square root n elements on the top? Then, of course, I'll ask for do the search in the lowermost one, and now you have to scan all the elements in the upper level, and there is more than square root n of them. So like it's balancing between two terms, and the sweet point is just in square root n. Clear?
If there is tree level, it could be n power 1 over 8, right? Or 1 over 4.
Sorry?
Yeah, if we had to design a tree level skip list to have the
3 levels, then it's not 1 over 4. 1 over 4 will kill you because there is almost linear number of elements in level 4, in level 3, and if you are putting too many elements in level 3, then more than whatever is a correct number, I'll just do a search that will force you to go through all these elements. So, and that would be more, and if it's n over 4, then it's, in your case, n over 16. It's also linear.
not n over 4, I mean the square root of n and n power by 1 4.
That's what you meant?
On 4. Yeah. Is this for tree level? Worst case time.
I'll have to check, but I think that it's what I wrote originally. But I'll have to double check if it's, and we all agree that it's a square root of something. If it's, sorry, it's a root of something, I think that it's a root of 1 over 3 is a sweet spot. You're saying it's 1 over 4, and I'll have to check. I don't want to, I mean, I cannot lecture and think at the same time. Cannot do any of them at individual. Yeah. Question with what happened in homework 5. You were in homework 4. You were asked about a hashing, which is actually a very, very useful data structure. You have Tucson is very nicely designed geometrically. You have nice squares. Think about Manhattan. You have nice blocks separated between them, all of the same size, all on the grid. And I want a data structure that I'll give you the cell point. I'm talking about question, question 8. You have a grid. You're given a grid, and I need to hash all the points so that if I'll give you a query point in some cell, I want to know who lives that Pi, Pj, and Pk are all living inside this block. Who lives inside this block? And the query time here was order of 1 plus k, where k is how many people you're reporting, how many people live in this block. That is optimal in the output size. So and maybe the hint was that if we are trying to use the very same data structure that we used for the closest pair without any modification, something bad happens with the collisions. People that came to my office, I said, think about what can happen because of collisions. Collisions are unavoidable if you are using a hash table. So you'll have cell 1, 1, and you'll have cell 3, 0, and they are both in age of 1, 1 equals age of 3, 0. Collisions are unavoidable if you don't use perfect hashing. They'll happen with very high probability. Somebody will collide with somebody else. If it's good hashing, then it will not collide with many others, but it will not be perfect. So what should we do? Oh, what's the problem first? Let's think about chain hashing. if I'll just use a chain hashing and I'll insert P1, P2, P3, P4, that is, I'll insert, and P5. Then maybe in the same linked list, I'll have P1, P2, P3, P4, P5, all sit in the same list. And now I ask who lives inside this cell, and you're going to this cell of the table, this slot of the hash table, look at this linked list and just filter out the relevant ones. So far, it doesn't look too bad. But you just need to filter it out. That's exactly what you actually are doing in the closest pair. But in the closest pair, there is at most one point in every cell. What's the difference here? That now my query point, here is my query point in a cell that contains only 2 people. There are billions of people all live inside this other cell, so this linked list is extremely long, and you're expected to answer it in order of 1 plus k, where k is the number of people in your cell. You cannot afford to check all these other people that falls together with you. So the hack is very simple. How can I avoid it? I'll just say that I have collisions, but it's collisions between the cells. And in the same linked list, I'll keep, here are the grid cell. Grid cell 3, 0, with all the people P1 and P5 that lives in it, and grid cell of 1, 1 with a linked list of all the people that lives in it, which is P2, P4, and P3. Okay, and that's all. The question was not if you can solve it, but if you notice what's the effect of collisions on this when this is our input. And then you're saying if it's a good hash function, then the number of cells that collide is small, only a constant, so I can find the cells that I'm after in constant time, and then it's just going down the linked list of the people inside the cell. OK, back to stable marriage. Any questions on any? Back to stable marriage. Just to remind you, what is a rogue couple? Rogue couple in a stable marriage would be female I and male J, not married to each other. Each has a spouse, which is not for female I. Her spouse is not male J. However, she thinks of male J higher than she thinks about her spouse, higher on her list. And at the very same time, male J is in analogous scenario. He is married not to female I, but to different female, but do a different female. However, he would prefer female I over his wife. And they form an unstable couple. We discussed it in length last meeting. And we discussed the TMA, traditional marriage algorithm. And the TMA, we want to argue that it produced a male optimal matching. What was the optimal definition? Optimal, it's good enough that I'll write it. the opt female for Adam was, look at Adam's list. Adam's list. Here will be his top preference, female 1. Here will be the bottom 1, and somewhere in between, realistically, somewhere in between, there is a opt 1. Probably not his top, his first choice, but if we think about all the world of all the n factorial possible matchings between the males and the females, we look only at stable ones. Stable means no couple is rogue. Only at stable ones, she's the one that he will get. And now we need to argue, without putting any moral judgment beyond it, we want to argue that the TMA will produce the matching at which Adam will be matched with his opt. That is, the algorithm is that the TMA that we discussed, mornings, evenings, crossing out females, and so on, and where it nailed down to, it boiled down to was that every female will only marry the best male that proposed to her. Not all the females that she can get, but only among the ones that proposed to her. So we want to say that under this algorithm, every male will be married to his optimal female. So let's assume that there is some case at which Adam proposed to his optimal female. Let's say that Florence is Adam's optimal female, and Florence rejected Adam. Now, rule of the games, rule of the TMA was that if Florence rejected Adam, it's because somebody that she prefers over Adam just made a proposal, or has made a proposal to her, not necessarily just. And somehow I'll break the time so that there is no two proposals that happens exactly at the same day or at the same time. So there is no two proposals or two rejections that happens exactly at the same time. I'll break ties some arbitrarily. So if there is a male that was rejected by his opt female, let's say that Adam is the first one. Everybody else was not rejected by their opt female yet. Okay. So why did Florence rejected Adam? Remember, Florence is his optimum, meaning that there is some other matching that is stable in which Florence and Adam are married. Otherwise, I cannot say that Florence is Adam's optimum. If she is his optimum, there is some other matchings, maybe not the TMA, at which they are married. So Florence rejected Adam because she has a proposal from Bob. To remember the names, A and B. Rejected A in favor of B. Now, Bob, let's look at Bob's list. Did I have the Florence? Yeah. Let's look at Bob's list at this moment. Florence rejected Adam. Adam proposed to Florence and got rejected by her. The algorithm was Adam goes down his list from his top preference, down, 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 and Florence is his top. Nevertheless, Florence is his opt. Is his opt. Nevertheless, she rejected him to maybe Bob. It doesn't mean that she'll eventually marry Bob, but she'll marry either Bob or somebody that she prefers even more, higher on their list. At this very moment where Adam was rejected, what's the scenario about Bob? maybe Bob was already rejected by some females, but he was not rejected by Bob's optimum female. He was not yet rejected by his optimum female. Adam is the first and the only one so far that was rejected by his optimum female. So where is Florence with respect to his optimum? Bob, like any other male, starts from the first choice and go down his list every time that he got rejected. So where is Florence with respect to his optimum? Two options. Either she's actually his opt, or Florence is higher than his opt. And maybe later he'll get rejected, but not yet. Either case, Florence is not below Bob's opt. Either she's the one, she's the opt, or Florence is actually higher than Bob's opt. That's the only assumption that we need. But we are absolutely sure that in Florence's list, when we look at Bob and Adam, Bob is above Adam. Maybe not next to each other, but she prefers Bob's over Adam. Now, assuming by contradiction that Bob was rejected, as we say, that Adam, as we said, was rejected by Florence, who is his opt. But if we want to assume that she is his opt, then there is some other parallel universe at which Adam and Florence are married to each other, and they are a rogue couple. And this other matching S is stable, no rogue couples at all. I want to convince you that no, that there is a rogue couple in this other universe as well. Right? Who is this other rogue couple? Not too hard to figure out. This other rogue couple is Bob, because Bob is married to somebody in the parallel universe, F2, but where is F2 in Bob's list? Now, if she cannot be higher F2, his wife in this parallel universe, the parallel universe is stable, she cannot be higher than his opt, because then it means that he can get somebody above, higher than this one, as his opt. F2 cannot be higher than his opt. It's stable marriage. Opt, by definition, is the best that Bob can get in any stable world. So F2 didn't want to give her a name. The wife of Bob in the parallel universe is below his opt, and definitely below Florence. Florence, we said, is either his opt or even better than his opt. Talking about Bob. So F2, the wife of Bob. How do I know that F2 is not Florence? In S, because in S, Florence is married to Adam. So Bob cannot marry Florence. It's one-to-one marriage. So Bob is married to somebody that he prefers less than Florence, possibly less than his optimum. And now putting all of it together. Here is your rogue couple. Looking at Bob, he prefers Florence more than his wife. Florence is higher on his list. In S, in the parallel universe. What about Florence? She already proved that she preferred Bob over Adam, her husband in S. They are not married to each other, but they prefer each other over their spouses. So they are a rogue couple. So it's contradiction. Contradiction to what? Where did we get to all this scenario? We got to it because Adam was rejected in the TMA by his optimal female. Conclusion, his optimal female, Florence, will not reject him in the TMA. QD. So we saw that the TMA, traditional marriage algorithm, is male optimal. Every male gets the best he can get in any stable world. So the unfairness is only halfway discovered. Everybody is good with the theorem. It will take a few passes until it all landed about what is contradiction to what. We already saw the example last meeting that the stable marriage is not necessarily unique. Sometimes it is. Depending on the preference list, sometimes there is only one stable marriage. Not too hard to discover such a case. But sometimes there is several matchings and they're all stable. So that's how I was able to look at who Adam get in per every stable matching and specify the optimum. And sometimes he'll marry the optimum, especially if it's a TMA that dictates what is a stable marriage. And let me step back one step. We described two algorithms to find stable marriage. Right? We described one algorithm that was a TMA. We discussed the version where we are using the TMA but switch the orders of males and females. And then we said, here is another very inefficient algorithm to find other stable marriages, other stable matching. When I'm saying stable matching, I mean each and every person is married to somebody and it's one-to-one. So here is another algorithm. Run through all the n factorial different matchings. And for each one of them, check if it's stable or not. Not very efficient, but you can, where I'm trying to get you is to understand that there are other ways to find stable matchings that are not the TMA algorithm by itself. That being said, I can ask, who is the optimal male for Florence? And to find who is the optimal male for Florence, it's very easy. I'll switch the rules of the males and females in the TMA and run it, and I'll find who is the optimal male. But now I'm asking a different question. Out of all the possible stable matchings, who is the worst male that she's getting? Now, but it might be her bottom one, the last choice, possibly. But possibly it's higher because she in every, if we'll try to match her with her last choice, it will be unstable. But unstable is not depending only on her and her husband. It depends on who else is married whom. It's some information that involves everybody. So I'll define the pessimal male for Florence as the lowermost one in her list, the last one that in any one of the n factorial matchings she can get. Okay, the worst she can get in any stable world. We say that the TMA is male optimal. Now I want to make this message even stronger. I want to say that it's female pessimal. Every female will be married to, if we're using the TMA, by her absolutely worst male that you can get in any stable world. So why is this true? Assume that it's not true, and we know that the TMA is male optimal. And now I needed names of bad characters, so I looked at movies that I remembered at the time, and yeah, I came up with a few negative characters. So let's think that Syndrome and Florence is some couple that is generated by the traditional marriage algorithm. Male and female. Male makes proposal, females are. Okay. And assuming that there is some other matching, S, which is also stable, in which Florence is married to Zod, and Zod is even worse than Syndrome. I'm trying to tell you that Syndrome is the worst that Florence can do in any stable world. Assume by contradiction that actually she can be matched with somebody worse in a different stable world, not what the TMA is producing. Okay, now it's simple. So in S, Florence is married to Zod, and in Florence's list, Zod is below Syndrome. So what happened in S? Syndrome, same guy, that in the TMA he is married to Florence, and she is his opt. To whom is he married in S? Could he married in S to somebody that he prefers over Florence? No, because S is stable, and Florence is, we already established, the best he can get in any stable world. His wife in the parallel universe in S cannot be better than his opt, which is Florence. So, and it cannot be Florence because Florence married Zod in the parallel world. So where is his wife in S? In his list below Florence. And you see why S cannot be stable. Because Syndrome will say, I prefer Florence over my wife in S. Florence will say, I prefer Syndrome over Zod, who is not, because I'm married to Zod, but I prefer Syndrome over my husband. So they form a stable couple, a rogue couple, unstable couple. And I try to convince you that S is stable, but it's not. I just put to you that there is a rogue couple in S. So it conclusion that such a matching S, such a parallel universe exists. And the assumption that it exists was because we assumed that Florence will get anybody worse than Syndrome in some other matching. So in the TMA, she will get her absolutely worst that she can get in a stable world. Okay, and that's where we end this this chapter about a stable marriage. Summing it up, we defined what are a rogue couple in a matching. We defined the TMA algorithm, where one side was making proposals, another side was rejecting or accepting. We proved that it produces stable matching. That essentially was the only good thing that I can say about this matching. We proved that it always terminates. It always ends in n square time, or n square rejections at most. It can end quicker if there are no rejections. Yeah, and we proved something about optimality and pessimality of it. Here, now, a very natural question that comes here is about the roommate problems. Roommate problems is much less polarized than this problem. Roommate problem is just said you have a list of n people. Each one rank every other person in terms of preference, and let's divide them into pairs so that there is no rogue couple. And couple doesn't involve gender in any way. It's very natural problem. The question here is that it's not clear that there is any stable matching under this definition. You can easily create a scenario at which if you play with rejections or any other algorithm, you'll figure out that there is no stable pairing given this preference list. So the roommate problem would be much more, yeah. So as I said, the problem is that it doesn't necessarily have a solution. And there are a lot of works about can you or can you not figure out if there is a stable solution or not. Solution with no rogue couple. And of course, TMA has plenty of algorithms around it, optimizing more parameters, a version that I'll be happy to discuss again, that I worked for a lot of time and got some partial results. We have a few papers about it, would be the following. I'll assume that in the IQ test and in the earning test, it will be natural that every person will prefer his or her spouse to be as high as possible in both these terms. That is, here is one person. Let's make it one male, just for no, just because, yeah, a person over here, and here is IQ, here is the earning. Do I need it to be male? No, it can be anywhere. And now I'm trying to ask is the opposite. And it's natural to think that everybody will like their partner to be as intelligent and as rich as possible. But now we're asking, how do you compare ones against each other? And then I'll ask, here is a vector for V1, V2, V3. We'll say V1, which is alpha 1, beta 1, is how person 1 from one gender weight these two properties when they rank people. That is, if I'll tell you about V1, what is alpha 1, beta 1, then in the parameter for this person is x1, y1, then V1, the person of V1, will score P1 as alpha 1 x1 plus beta 1 x y1. And if this person is Pi, which is xi, yi, then how V1 rank Pi would be alpha 1 xi plus beta 1 yi. Okay, so my input is just of linear size. It's just every person told me her or his earning and IQ, and told me how they weight these properties on the opposite gender. And now, given V1, one person that we picked, tell me how do I pick V1's first choice? Extend it a bit. Of course, how do I, since V1 only use this vector to normalize or to rank the other people, here is a vector V1 and assume that it's unit length. And here is the direction of V1. And you should all tell me who is, out of all these points, how do I find the point that is the first choice of this person? I know what you mean, yes. It's, remember linear programming? What is our cost function here? I look at V1. My cost function is determined by alpha 1, beta 1. I'm looking at a line orthogonal to V1, my line which is too complicated. Line which is orthogonal to V1, and I move V1 all the way from infinity until I hit one of these people. And that would be my first choice. And then my last choice would be moved this line parallel to itself all the way until you get to the end. That would be my lowest choice, or V1, lowest choice. Okay, and you see where it's going. So my input is only n squared. It's only linear size, just a few parameters. It's very natural. And it's my, it's even, yeah. And there are good reasons to ask how fast can we find matching, or how many probes in terms of you had a date with one of the other people, how much can I learn about your own preference from saying I rank this person over this person because of these properties, how much can I predict your future preference of other people. and so on. There are a lot of questions that comes up from this problem, assuming that there are not necessarily two and not necessarily these ones, but that there are a few properties that you weight one against the other. Okay, but the cute and little theoretical question is over here is, can you beat the n squared time running time if you find a matching where this is your input? So there is no point of asking you, can you beat n squared running time for the stable marriage problem just because the input size is n squared. Just to read all the preference list already takes n squared time. So obviously I will not ask for better running time over there. But I can ask the very same question if my input is smaller. Okay, moving along to dynamic programming. Big topic, will not cause you to like me more, to give better evaluation. It's not an easy to teach topic. So not an easy to teach, will not necessarily cause you to fall in love, but it's just important enough that I cannot really avoid it completely. How long are we staying with this topic and how fast is up to you? But if at least a few examples we have to cover. So dynamic programming is a method like greedy algorithm, like randomized incrementals that we saw in the linear programming. Dynamic programming would be a methodology or a paradigm that we are using in many types of algorithms. And to summarize it, it will say, I'm not sure yet what is my global optimum solution would be, but I'll keep all my options open. And the best example of dynamic programming that I know would be in Dijkstra. So Dijkstra algorithm, hopefully most of you know about Dijkstra, but just to remind you, you're given a graph G of VE. You'll assume that the weights of all the edges are positive. Otherwise, Dijkstra doesn't work. And I'm asking you, find in this graph the optimum path, the minimum weight path that starts at S and ends at T. And the algorithm progressed, maybe we'll go deeper into Dijkstra, but the algorithm progressed by finding the distance D of V1 for some vertex V1 in the graph and compute the optimum distance D of V2 for another vertex V2 in the graph, which looks a bit unnecessary. Like, I just want to find one shortest path from S to T. Why are you computing the distances to a lot of other vertices? And the algorithm says in return, if I know what is the shortest path from S to T, I will not go any further. Then I don't need to bug you with other distances. But if I don't know yet what is this shortest path, I don't know what is the shortest path yet, then I'll still compute the shortest path to a lot of other vertices, V2, V3, V3 over here that I'll compute the shortest one. Why? Because as the algorithm progressed, one of them will grow up to be the shortest path all the way to T. And at earlier stages, when I just know the shortest path to a few of the vertices, I don't know which one of them will stand up to go all the way to T. Kind of my supervisor was saying that it's very hard to predict, especially the future. So I don't know which of these paths will turn out to be the optimus path to T. It's chicken and an egg if I would know which one. If I would know if V1 is on the shortest path or T or not, then I can save a lot of work, but my job right now is to find who are the vertices that are on the shortest path. So that's why I compute the shortest path to all of them, but why? Why is this so relevant to the global shortest path of all the paths from S to T? There is a very important observation that we are going to use 5, 6, 7 times during this course. The important observation is that I don't know what is the shortest path from S to T. However, if your shortest path does go through V3, your shortest path to T does go to V3, then the first part of the path all the way to V3 will stay the same. Even though you want to find the shortest path to T, it's not an effort that is useless to compute the shortest path to V3, because if it will turn out that V3 is part of the shortest path, then the portion of the shortest path from S to V3 that I'll use in the big path will be the same portion that I already discovered. So it's data that I will recycle, but which of all the pieces of items that I compute will turn out to be useful for the big problem, I don't know yet. I'm solving smaller problems and then a bit larger problem and that's a bit larger until eventually I find what is the shortest path all the way. It's a graph setting. I compute first the distance from S to itself, which is 0, if all the weights are positive. Then what is the shortest path to very nearby vertices, shortest path to further and further and further away, but I'll make sure that the distances that I know all this time are indeed shortest path. Okay, so that's kind of my best example of where dynamic programming is used. But let's see a few less obvious examples. So if you open CLRS and look for dynamic programming, the first example that comes into mind will be in finding the longest common sequences. So classical example, let's talk about this example. And show me hands. How many of you know already the LCS? Look, longest common subsequence algorithm. Anybody? Excellent. One. That's enough. Okay, first, what is my problem? I look at a string, A, B, C, D, and I want to find a subsequence, not to be confused with substring. I want to find a subsequence of this string, of this sequence. How can I do it? I take this string and I can delete some characters, but I'm not allowed to change the order of any characters. Okay? Don't change the order, but delete whomever you want. So you can delete the A at the end, being left with A, B, C without the A in the end, or delete this C, or delete, sorry, the B, staying with A, C, C, or delete everything in between, and so on. But, or don't delete anything, and then you are left with A, B, C, A, the original string. You can delete everybody. Empty string is also a substring. But A, C, B, A will not be a subsequence, because if there is B, C, then I switch the order, and I'm not allowed. Another important definition is what is a prefix of a substring, including its notation. If I have this string x, then x from 1 dot m just implies takes the first m characters of your string. 1 dot m takes the first m characters of the string. Okay. So x from 1 to 4 is this whole string. X from 1 to 1 is just A. And we will actually use this notation, x from 1 to 0, it's just an empty string. Don't take any characters. So in prefix, you only delete characters at the end. And in subsequence, you're deleting characters anywhere you want. What is the LCS problem? You're given two sequences, each with m and n characters. And you are trying to compute what is the longest common substring between these two characters. That is, generate a substring of x, which is also a substring of y and has as many characters as possible. And since we like geometric algorithms, I like geometric algorithms, then the geometric interpretation would be as follows. Write x on a line, write y on a line, and now you can put segments between different characters. However, you can put a segment, red segment, only between two characters which is the same letter. You cannot connect A to B. You can connect B to B, but you're also allowed to connect this B to this B. That's also illegal. So first constraints about these red segments is that they are connecting a letter to the very same letter. Second constraint, it's one-to-one. This B cannot be matched to both B's at the top, either to this one or to this one, but not both. And the third constraint is this one. You're not allowed crossing segments. Okay. I cannot, if I connect this B to this B, then notice I cannot connect anybody else, because any other segments will cost the two B's. The long segment that I'll connect the two B's with to cross anybody else. So the length of my matching, the number of characters that I was able to match, will only be one. You match this B to this B, the length of your LCS is just one. On the other hand, if you match this B to this B, it doesn't contradict matching this C to C, these two B's to each other, and these two A's to each other. So the length of the LCS here is 4, which is arguably the longest that I can find with this input. Okay? So, and the question is sometimes find n LCS, sometimes find if there is more than one LCS, and so on. But we are aware that the LCS is not unique in general, and there was one course that it became the CS4 for one semester that it became the 445 salute. And this is a figure that I got because one of the students wrote it on the exam, and I liked it enough to. Yeah, so easy solution, brute force LCS. How many subsequents of X can I generate? How many subsequents of X can I generate? Well, I need for every characters of X to say, are you in the subsequence or not? Yes, no, it's a flag. I do it for every character, so I have 2 to the power m many decisions to make, number of subsequents that I can generate. Of course, the same subsequence maybe is generated more than once, but that will be the maximum number of subsequents that I generate. And for each one of them in linear time, you can find if it's also a subsequence of Y. Yes, no, not what's the longest, but for each subsequence that you generate from X, is this also a subsequence of Y? That's a simple greedy algorithm. Check the first against the first and move on. So that's a very slow algorithm. The simplification would be, what do I do in the case of the shortest path in a graph? Somehow, V over here somehow I computed the shortest path, or what I suspect is the shortest path to V2, and then I realized that from V2 to U, there is an edge, and the cost of this edge is $10. So I can say the distance to U will be, I can guesstimate it to be the distance to V2 plus $10, and guesstimating the cost or the length of a path is somehow easy to communicate between different nodes. What will be much harder to communicate between nodes? If V2 will tell you, here is the shortest path to me, including all the vertices along it, so now add me at the end of this list, and now you're looking at the distance. To you as a much longer list, and now start to handle the whole list of vertices. Where I'm going with this analogy is that communicating cost or numbers between the nodes is easy. Communicating the whole solution, the whole set of vertices will take a lot of time. That's the reason that in Dijkstra, like all the dynamic programming algorithms that I know of, and definitely all the ones that we'll cover, I'll compute at the first iteration what is the cost of the shortest path to t, and I'll completely put under the rug the problem of what is the shortest path itself. Who are the vertices along the shortest path? That is the driving direction. You want to go from here to Phoenix, what is the driving direction along the way? I'll first compute what is the distance to Phoenix without ignoring completely the question of what is a navigation direction. Only when I'll find the shortest path, I can backtrack my way and reconstruct who is actually on the shortest path. And it will always be from the end to the beginning in the reverse time. Essentially, we are going to do the same thing in the LCS. I'll ask what is the length of the LCS that I can get, and once I know what is the length of the LCS, I'll ask who are the characters that are on this LCS. But it's always this two-steps process. First the price, and then backtrack to actually who are the items that got you to this optimal price. Good class. Thank you.